Hey guys, this is Alex, and I want to make a video for you today about discovering mathematics, or at the very least discovering new connections in mathematics. I think this video is important because I think that play is a really important part of math, and I don't really think it was emphasized in my education. And I think that you can get pretty far by taking a known phenomena and just tinkering with it and looking at it from new perspectives and interesting ways uh, until you come to some pattern. And that's what I want to do today. So our example comes by way of a poker player. His name is David Sklansky. And Dave Sklansky used to, when he was playing in a poker tournament, he would give his fellow poker players a sort of salacious math idea and see which one of them was intrigued by it, and that would maybe tell him a little something about how they think and possibly even how they play poker. So his idea was, did you know that the sum of consecutive cubes is always a square? And I don't know what this says about my poker playing ability, but I was intrigued enough by the statement to take a gander at it. And I'll include the proof for it at the end of this video, but I don't want to get bogged down in the proofy details just yet. I want to focus more on the kind of creative aspect of play. So just to explore it a little bit, the sum of consecutive cubes always equals a square. Okay, so we have 1 cubed, that equals 1 squared. That's easy enough. Then we've got 1 cubed plus 2 cubed. Well, that equals 8 plus 1 is 9. That's 3 squared. 1 cubed plus 2 cubed plus 3 cubed is 36, is 6 squared. And 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed is 100, is 10 squared. And so on and so forth. So you can keep going like this, and it seems like it will always continue. So naturally curious about this. The way I like to look at this stuff is sometimes I'll try and make it physical, and ultimately we're dealing with kind of a transformation. So if you can make a transformation into a physical form, it can only help you understand it better. So what I did was I actually made a series of blocks and put them into cube forms. And so let's just visualize the transformation. One cube can be translated into a square just by looking at it from a 2D perspective. Simple enough. If we add 2 cubes, 1 cube plus 2 cube, that can be translated from a series of cubes into a square by rearranging it as such. And then we have a 3 by 3 square. And likewise, if we add another cube to the mix, 1 cube plus 2 cube plus, 1 cube plus 2 cube plus 3 cube, we can add these guys in and rearrange it such that we again get a square, 6 by 6. And again, if we add another cube to the mix, a 4th cube, we can rearrange it. We can rearrange it such that we get a 10 by 10 cube. And this was pretty fascinating for me to see, and it made me start to want to look at transforming it in other ways, looking at exploring different transformations for this. So some of the ones that I explored were, well, what if we kind of stack these things as if they were a pyramid? That might be me kind of interesting, and stack them this way, and maybe we can look at the ratio of the width to the height, or something kind of interesting about the angle. Perhaps you could try and stack them this way and run the angle from the inside of the box up through here and so forth, and see what that angle looks like. But the transformation that I ultimately landed on was one where I kind of took the cubes and I sort of sliced them like this, and then like this. And so on like this. So we'll bring this over a little bit. And my first instinct was to maybe look at this as a pyramid, but I quickly found out that the more interesting way to look at it was to look at it as a right angle. And so we smush these together and bring them over to the left here. And the initial question that struck me is, well, we've got this right angle. I wonder what the hypotenuse looks like. And the first thing that struck me is that this 1 cubed and 2 cubed together, if we just looked at those two for a minute, that creates a 3, 4, 5 triangle, such that if we lay 5 cubes on an angle, it would match up perfectly. So the next logical question is, how many more are like this? Are there any more like this? So that requires that I kind of systematize this a little bit, and I can only glue so many cubes together. I need to find out a better way of generating more of these so that I can see if there are more such instances where we get an integer hypotenuse. And so looking at this, the first thing I can see is that, well, this side here is always going to be a square. It's the square of the number of cubes that we're dealing with. So if we just look at these two, we've got 2 cubes and we've got 1, 2, 3, 4, 2 squared. Same here, we've got 3 cubes and 3 times. And 4 cubes, we've got 4 times, and that will always continue. So this bottom one is I, where I is the number of cubes squared. And this top A side, so if this is A, B, C, this A side is going to be 1, 2, 3, 4. This looks like a triangular numbers. So the formula where I, again, is the number of cubes. So that's convenient. In terms of I can represent the base, and in terms of I can represent the height. So this is, bring this over. So this height is going to be I times I plus 1 over 2. That's just the formula for a triangular number, where I equals number of cubes. And this base is going to be I squared, where again, I is the number of cubes. So now that I've got some systemization and a formal way of representing this transformation, let's take to Python and see if we can generate these. So we come here. And I already wrote up a definition called newpers for new perspectives. And it passed it some number of cubes that we want to do this transformation on. I substitute n for number of cubes just to make the formulas look a little bit nicer. So the A side that we just looked at is n times n plus 1 over 2. That's just the triangular number. B is n squared. And our hypotenuse is the famous a squared plus b squared square root. And if that hypotenuse is an integer, then return n the number of cubes, side length a, side length b, and the hypotenuse. To loop over this, I wrote a small little run function that says for I in the range of a big number, run this function on that I. And if it exists, that is, if it's an integer, then print it out for me. So this will show me all of the other cases. So let's go here and run. And the first thing that we see is when we have two cubes, we get a 3, 4, 5 triangle. And the next such instance where, let me just cancel this. The next such instance where we have a cube that when we do this transformation to, we have an integer hypotenuse is 15. 15 cubes will give us an integer hypotenuse. Same after that is 104, 714, and so on. And so now we have kind of an interesting sequence. And the thing that I always do when I find an interesting sequence is I go to the Online Encyclopedia of Integer Sequences. Online Encyclopedia of Integer Sequences. And I type it in. So this is a repository, wiki, database, all of the above, of a bunch of integer series. And whenever you find something interesting involving that integer sequence, you post it under the sequence, and they give them all identifying tags. And it's a nice way of keeping track of things and finding connections between different parts of mathematics. So let's type it in. We've got 0 is the first one, 2, 15, 104, 714, 4895, and 33552. That should do it. And lo and behold, it's already been discovered. And the first thing that struck me when I saw this was Fibonacci numbers is apparently an alternative way of generating this this sequence. And that's really fascinating to me because I mean, Fibonacci numbers are you start with 1, 1, and then you add them up, you get 2, and then you add the previous 2. 1 plus 2 is 3, 2 plus 3 is 5, 5 plus 3 is 8, 5 plus 8 is 13, and so on and so forth. That's Fibonacci numbers, and we didn't do any of that when we were doing this cube transformation. At no point did anything remotely resembling Fibonacci numbers, at least to my mind, show up in there, but yet Fibonacci numbers of 2n and 2n plus 1, multiply those two together, and you can generate the same exact sequence. And to me, that's fascinating. So given that, the next thing that I saw was, well, let me say this. I looked through this already, and I didn't find any mention of this this cube to triangle transformation that I did, and that kind of prompted me. Well, let's look at the hypotenuse sequence that we have. We, after all, have another sequence. So we'll go here and we'll type in. Starts with 0, 5, 255, 12116, and 570129. And that one hasn't been seen before. So now this, in a way, kind of confirms to me that we've stumbled onto some new and interesting connection, because if someone had found this sequence, I think that they would have written something up in the Online Encyclopedia of Integer Sequences. It's just a nice way of keeping track of things and really taking credit for it as well. So there we go. I mean, we found, just by taking a known phenomena and tinkering with it and trying to look at it in a new perspective, we've kind of stumbled onto, I mean, it's not proven, obviously, it's just a conjecture, but we've stumbled onto some interesting rabbit hole that might yield some new and interesting mathematics. And I mean, it's not exactly grandiose, but that's okay. It's interesting enough, and not everything has to be grandiose to be satisfying. So the next thing that I did and was try and generate some kind of recurrence relation, or try and figure out a way to generate these in a better fashion than just this brute force loop that I'm doing. And so what I did was open up Excel, and just type these numbers in. So we'll go 0, 2, 15, 104, 714, 4895, 33552, 229970, 157, 6239. Okay. And the first thing I did was I said, well, let's just, and this is just me randomly doing stuff. Sometimes it works out, sometimes it doesn't. You just have to play with it for a while. But I said, let's look at this guy divided by that guy, and go all the way down the line. Okay. First thing I noticed is that it seems to be converging on a number, and that's kind of nice. And the number is between 7 and 6. So I said, okay, well, let's just do this previous number times 7, and cancel, and let's send that down the line. And it looks like this number is pretty close to that number. This number is pretty close to that number. This number is close, but it's a little bit further off, and same thing with this one. They're all pretty close. So let's just take a second and look at the difference between those two. Equals that minus that. Whoops. Minus that guy. Okay, and we'll send that guy down the line. Okay, so, it looks like this guy is, this guy is one off from this guy, and this guy is one off from that guy, and this guy is one off. Oops, this guy is one off from this guy. And it looks like they're just one off. So, So what we can do then is we can say equals 7 times, whoops. So this guy this 15 right here should equal 7 times the one before it, minus the one before that, plus 1. Plus 1, since it's different, the difference between these guys is just 1. It's just 1. So we enter that in, and we drop it down, and lo and behold, it looks like they all match up. Okay, so we've got a recurrence relationship. Let's insert a text box. We've got a recurrence relationship. F of n plus 1 equals f of n minus f of n minus 1, that's that previous guy up here, plus 1. And there we go. Now with this, a recurrence is nice, but really I'd like to have a closed form equation for this. And what I would do is I would go to Wolfram Alpha, since I'm not so skilled at turning recurrence relations into closed form formulas, is I'm just going to go solve, input my recurrence relation, and then give it some cases, some known cases. So f of 0 equals 0, f of 1 equals 2, f of 2 equals 15, and f of 3 equals 104. Let's put it in. Let's ask it to solve. It says no solutions. That means I messed up because I did this before and I know that it has solutions. F of 0 equals 0, f of 1 equals 2, f of 2 equals 15. Oh, I know what I did. 7 times f of n. F of 3 equals 104. Put that guy back. And lo and behold, we have our closed form equation. And the closed form equation could be helpful for one, trying to prove that this equation will always produce an integer, such that when you do this when you do this transformation to it, that it'll always yield an integer hypotenuse. So that's one way that this could be useful. And the other way is to try and show that this equation equals the Fibonacci of 2n times the Fibonacci of 2n plus 1, if you can find closed form equations for that, and show that these two are equal to each other. That could be interesting as well. And between the two of those things, if we could prove those, and to be sure, I can't prove those things, and I would love it if one of you guys watching could make an attempt at proving those things, and if you find it, please do get in contact with me and show me how you did it. Yeah, it's just, again, just a playing with math and finding interesting excursions to go down and interesting rabbit holes, exploring them, and trying to look at the same phenomena from a new perspective. And I think that that's an important part of math that, again, just wasn't really emphasized in my math education, but is nevertheless super valuable in advancing the field. Well, that's all for my video, and thank you guys for watching, and please leave me some comments below and tell me what you think. All right, bye. Hey guys, welcome to the video where I prove that the sum of consecutive cubes always equals a square. Let's start off with a few examples just to wrap our head around it. 1 cubed equals 1 squared. 1 cubed plus 2 cubed, that's 3 squared, 9. 1 cubed plus 2 cubed plus 3 cubed is 27, and 9 is 36, is 6 squared. And 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed is 100, is 10 squared. So we can generalize this a little bit and write 1 cubed plus 2 cubed plus 3 cubed plus ... plus n cubed equals some number squared. And to take a little bit and try and figure out what this mystery number is, let's look at the output here. Let's look at the output here and try and see if we can come up with a pattern. And the first thing I see is that 3 is 1 plus 2, and 6 is 1 plus 2 plus 3, and 10 is 1 plus 2 plus 3 plus 4. So it looks like these are triangular numbers. So we can rewrite this as 1 cubed plus 2 cubed plus 3 cubed plus ... plus n cubed equals n times n plus 1 over 2 squared. And now to prove this, we're going to use proof by induction, and we assume that this hypothesis is true, and then we try and prove it for the n plus 1 case. And if we can prove it for the n plus 1 case, then we will have proven the theory, just because we already have our base case. So let's write it out in n plus 1 form. We've got n plus 1 times n plus 1 plus 1, all that over 2, and all of that squared. And that's going to equal 1 plus 1 cubed plus 2 cubed plus 3 cubed plus n cubed plus n plus 1 cubed. So that's the same formula represented as n plus 1, and let's see if we can simplify this a little bit. This first one, we can rewrite this guy as n plus 1 times n plus 2 over 2 squared. And that's going to equal, well, we know that, let's do that color. We know that this part equals that because we assumed it to be the case, and that's part of our assumption. So we can just rewrite this as n times n plus 1 over 2 squared. So we've got n times n plus 1 over 2 squared plus n plus 1 to the third. N plus 1 to the third. Okay, so far so good. Let's try and simplify this a little bit. This inside region, we've got n squared plus 3n plus 2 over 4, and this part is squared. That's just expanding the n plus 1 times n plus 2. And that's going to equal n squared plus n over 4, that guy is squared, plus n plus 1 to the third. And we can get rid of this 4 in the denominator just by multiplying it out. So n squared plus 3n plus 2 squared, that's going to equal n squared plus n squared plus 4 times n plus 1 to the third. All right, so if we try and do this multiplication, this one's going to come out to n to the fourth plus 6n to the third plus 13n squared plus 12n plus 4. And this right-hand side is going to be n to the fourth plus 2n to the third plus n squared plus 4 times, and we FOIL this inside part, n to the third plus 3n squared plus 3n plus 1. Multiplying this side out, we get n to the fourth plus 2n to the third plus n squared plus 4n to the third plus 3 times 12n squared plus 12n plus 4. And we'll combine some like terms. This one, we've got n to the fourth, then we've got this guy and this guy, plus 6n to the third, plus this guy and this guy, that's 13n squared, plus this guy, 12n plus 4. And if we look at these two, we can see that n to the fourth, 6n to the third, 6n to the third, 13n squared, 12n, 12n, 4, 4. These two are exactly the same, and so we have proven our case. We've shown that they're the same thing, and thus it's true for all cases that a sum of consecutive cubes will always equal a square. Thanks for watching, guys, and see you in the next video.